Hey everyone, I want to thank you for allowing me to redo Class 17 handout. I think it will benefit everyone because I'm simplifying the second reaction, the allylic halogenation, which is reaction 18B, but also now both sections have exactly the same information for this very important handout, which introduces us to radical reactions. I believe you've already watched the first video where we talked about page 1 of this new handout, and I took a look at the photograph of my model with all the p orbitals. Let's look at what page 2 has. Page 2 talks about allylic position, which is very special. It's the carbon next to the double bond, and it's special because when you have a radical or a carbocation that's in the allylic position, then it can undergo resonance. So take a look at this. I didn't do this in class for either section, I don't think. Let me draw the mechanism arrows and the result. Now this would not happen if the radical was in a different position, a non-allylic position. And I have space up here. The result is the double bond shifted, and now my new radical is there. We've seen this before with carbocations. For instance, you could shift this pi bond over like that. Did you notice that it only takes one arrow? Because I'm moving 2 electrons in a normal mechanism arrow. But for radicals, you're using fish hooks and you're moving only 1 electron for each arrow. And so I have a new plus charge right there. So this allylic position is super special. It's a stabilizing position, right? The carbocation is more stable because of resonance, and there's resonance because it's in the allylic position. Same thing for this radical. The first reaction that we saw on Friday was radical halogenation of an alkane, and I want to emphasize alkane. This is the only reaction that we... Do I keep saying reaction 18? I mean reaction 17A. Allylic is reaction 17B. But for this reaction, this is the only reaction I will ever give you where we start with an alkane. And so if you're wondering what reagent I should use, well, if you have an alkane, you have to use Br2 in light or Br2 in heat. Light, again, H nu, the Greek letter nu, is the energy of a photon, and that's why we use it as a symbol for light, H nu. This one is heat, the triangle. You have to find a hydrogen to remove and replace it with a Br. Any hydrogen I remove on this ring will give me the same product, which is this. Now, what if you have carbons that are different substitution, primary, secondary, and tertiary? Well, we are going to remove the hydrogen off of the most substituted carbon that has a hydrogen, which is this one, tertiary. You know, there is no hydrogen if the carbon was quaternary. And we're going to replace that hydrogen with a bromine. You do need to know the mechanism. We'll go over that next. The reagent selectivity literally is you put the Br, replace a hydrogen that's on the most substituted carbon that has a hydrogen. Okay, so again, quaternary carbons can't have a hydrogen on them, so it would, in this case, it's a tertiary carbon. In this case, they're all secondary. It's not stereoselective. In the previous page, we talked about that the radical is an sp2 carbon, which is flat, right? And so hopefully that photograph helped a lot, but without the photograph, you have to know that that radical is flat. And there's a p orbital sticking perpendicular from the 3 sigma bonds. And the Br could come from the front or the back. So this is, again, not stereoselective, and if we need to draw stereoisomers, we understand that this carbon here is chiral, and the Br could come from the front or the back. Make sure you draw the methyl group in the opposite sign, opposite symbol. And here, now my bromine is dash. This is racemic. Okay. The mechanism. Let me do, I think I did the mechanism for this, for both classes. Let me do the one with the ring. It's actually simpler. And I'll go a little bit faster because you've seen this already once. And actually this is a second video where I'm doing the mechanism. There's one in the review folder where also this mechanism of radical halogenation of an alkane. I'm not going to do much talking. Let me just get this down first. And I'll put notes later. If you draw one hydrogen, you have to draw the other. And we're going to use the radical we just formed. We're going to do something called meet in space. So there's a bond now between hydrogen and bromine, but the second electron of this bond goes to the carbon. Okay. You're free to pause the video if you want to try the rest of it on your own. Propagation has 2 steps. Again, meet in space. Oops. Make sure your fish hooks are very clear. Okay. Try not to rush it, else your fish hooks are going to look kind of weird. And we form the Br radical, which can go back and start the propagation step over again. Again, I am going to annotate this after I'm completely done. There are 3 termination steps. It requires 2 radicals coming together. So we can have the 2 bromines come together, from Br2. We could have the alkane radical, or the cycloalkane radical, plus the Br radical come together. And we make the product again. So there are 2 pathways to make the product. Again, I'll add notes in a bit, but propagation is what we really want happening. We want a lot of propagation, not much termination. Because if we get a lot of termination, we'll get a lot of this last one, which is nothing for us. It's very rare that you want a molecule that has nothing, no electronegative atoms attached to it. This is just a hydrocarbon, only hydrogen carbon. Okay, the notes now. For the initiation, for the initiation, you need to put light or heat. And there's 1 initiation step. There are 2 propagation steps, and it's between a non-radical plus a radical. Take a look at what we have. Non-radical, radical, non-radical, radical. For the termination, there are 3 termination steps, and it's radical plus radical. This second step, the first propagation step, this is called hydrogen abstraction. Not proton. It's literally the hydrogen because we take one of these electrons with us. We leave one behind. So it's not a proton, it's literally the hydrogen atom with its electron. We form a radical that is, again, flat, meaning the bromine can come in wedge or dash. In this case, it doesn't matter because this carbon is not chiral. When we form the Br radical down here, it goes back to the beginning of the propagation and starts the process over again. And that's what we want. We want to keep going, keep this alive until all of this is consumed and converted into this. Now the terminations may not look too bad because if we form Br2 down here, we can just shine more light and get the process started again up here. So shine more light. And this is okay, but it terminates the propagation step. It stops it. But it stops because it doesn't create any radicals. It stops propagation because no radical formed. Okay, and then the last one is not good at all. It's very rare that you would want to make a hydrocarbon, and there's nothing we could do with this. We can't break it apart very easily. It siphons off a lot of our starter material going through this, so our yield goes down. This is making our product yield, right? Our theoretical yield, no, not theoretical, our percent yield goes down. Okay, all right. And so the idea is to keep radical concentration low to avoid termination. If we keep it low, that's fine, right? Because in this cycle, we always create one for every one that we used. So it will keep going, even if you start out with a low concentration of radicals. All right. That's all I want to say. That's a lot for page 2. Let me finish up page 3. It's just a couple more notes and some practice, and I want to do the practice so you have the answers. If you notice that the mechanism for a radical, it's like reading a text line by line. So the product that you made in the previous step is now the starter material of the next step. We are only going to use Br2 because the others, halogens or other dihalogens, there are issues. Like F2 is too exothermic, Cl2 leads to a bunch of different products, so it's not very selective, and I2 is too unreactive. But even for monobromination, Br2, we get a mixture. We only need to draw on any assessment, any exam, the major. So only draw the major. And this is for, again, just for this reaction. Radical halogenation of an alkane. Okay. Let me show you how quickly we could do these problems. Draw the product, consider stereochemistry. Okay, but on a scratch sheet of paper, I'm going to draw the products without stereochemistry. Okay, that's one of them. For the second one, without stereochemistry. Okay, so I'm going to ignore that wedge. You'll see why I'm allowed to do that in just a bit. And for this one, very simple, but I think we're going to get isomers for this one as well, the bottom one. For the first one, I have a chiral carbon here. And the BR, the radical looked like this. So when the BR came in, it could come in front or back, and we would get two different products. And the products would be racemic. I am going super fast. Go ahead and pause the video or wait till I'm done and then copy what you see. This is racemic. Try to understand how I'm getting these results. Okay, for this one, it's interesting that the radical intermediate is always going to be flat, meaning that this wedge doesn't matter. This molecule here is 100% S. Wait, yeah, S. Let me write that down. S. But because we made an intermediate that's flat, we are going to get 50-50 wedge and dash for my products. Wedge or dash BR and wedge BR. Racemic again. Okay. The last one. Oh, we should do the analysis on our scratch sheet of paper, right? That's chiral. This is chiral. So even when we don't have any initial chirality in the starter material, we have stereochemistry or stereoisomers in our product. Racemic. And let me finish the thought that I started for the second one. This one is S, and then we lose all stereochemistry, neither R nor S, totally flat. And then when we add the bromine, we get the first one, which I drew as R, and the second one I drew as S. 50-50. Right, 50-50. Okay, that completes page 3. We got up to here for both sections. It's where we started talking about the allylic halogenation, where I wanted to simplify it, and also I want to make sure that both class gets consistent information. So please watch those videos when you have time, the videos for pages 4 and 5.